Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to Power Electronics. This is Ryder Malki. Inshallah, we will take today lecture 7. Now, in lecture number 7, we will go through the controlled rectifier. And you can follow your textbook. This is your textbook. You can go through it in chapter number 4, section 4.3. And also I have given you a handout. You can go through the notes. Okay. Now in this lecture we will go through single phase full wave controlled rectifier. The previous lecture it was half wave. Now in this lecture we have full wave bridge controlled rectifier. I'm emphasizing on the controlled, ya shabab, because this is for the thyristor SCR. We are using SCR, silicon controlled rectifier. Today inshallah we will go through introduction, small introduction, and then we will see and analyze the circuit with inductive load, with the resistive load only. Then we will have to analyze the circuit with R load, with RL load, inductive load. And we will see the discontinuous current mode, and then inshallah we will go through the continuous current mode. We will see the difference between them in the waveform and the output voltage. After that we will take example inshallah. Now this is our circuit. This is the circuit for the rectifier circuit, bridge controlled rectifier. We have here S1, right? We have here S2, we have here S3, S4, same as the numbering of the SCRs, same as the diode. We number them according to their operation, the operation time. Now, let me just remind you with the operation here, shabab. Now this is our supply. As you can see here, we have here positive cycle, we have negative cycle, and then we have positive cycle, and so on. Okay. Now in the positive cycle here, shabab, we know that we are applying voltage to S1, right? And of course S1 now. Let me just emphasize on something, shabab, very important. We need to make alpha here is 60 degree in order to switch on the thyristor, right? So we need to trigger S1 and S2 now to be 60 degree. So if it is already triggered now, then a current will pass from the positive here through S1, because S1 now is forward bias, right? And it will go like this. It will not go from here through S3 because it is reverse bias. So it will go through the load from this side, so from the upper point. It will go through the load and it will come back here through S2, because S2 now is forward bias, right? And it will come back to the supply. So when we have the first positive cycle, we have S1 and S2 are working and triggered at 60 degree. That's why here the V out, shabab, can you see here, shabab? This is our V out. So after 60 degree, we will have a triggered voltage, right? And it will reach up to pi, shabab. Okay, so here alpha is 60 degree. Here we have pi, right? Here we have pi. Now this is for S1, S2. Now after 60, the second 60 degree, I'm going to erase the shabab. Now, again, the same condition, we have to have 60, the alpha should be 60 for S3 and S4. They should be triggered at 60 degree, right? Now, in case of the negative cycle, here يا شباب, as you can see on the right side, in case of the negative cycle, we will have here positive from the supply and negative here يا شباب. So the current will go from here up to this point. It will go through S3 because S3 here is forward bias, and S2 is reverse bias. So it will go from here through the load from the positive terminal, right? And it will go here. Of course, it will not go through S2 because we have here ايش يا شباب? We have charges. So this wire is fully charged with the positive cycle يا شباب, or with the positive signal. Now, after that, it will go from here through S4, and it will go to the supply again here. Now, this is for the negative cycle, okay? So S3 is going to be triggered, S4 is going to be triggered on, and we will have current going through them, right? So after 60 degree, can you please focus here on the right side, شباب? So after 60 degree, S3 and S4 is they are going to work, and it will conduct, and this is their voltage, this is output voltage, and up to here. This is one cycle. Now, this is for one cycle. That's why it is full or called bridge controlled rectifier, and it's a full wave because we are converting the negative cycle and the positive cycle, okay? In half wave rectifier, we are converting or rectifying just only the positive cycle, but in the full wave bridge, we will convert also the negative cycle, okay? Now, for the current, we can, this is our current, of course, but I will draw it here يا شباب. I'm going to use the green color. Now, in case of resistive load only, of course, the current, it will directly go, it will start from the upper point, right? From the maximum here for the current. So it will start from here up to 0 يا شباب. So it will be like this, okay, to 0, and then of course it will conduct after 60 degree, right? So after 60, the second pulse, it will conduct again up to 0. So this is for the current. This is for the current يا شباب. This is I out. Okay. Yeah, that's it for the resistive load. Now, this is the formula. Make sure you understand this formula. This is V max divided by before it was 2 pi, right, for the half wave. Here, divided by 1 plus cosine alpha, right? And this is the current RMS يا شباب. Of course, again here يا شباب, we need to make sure that alpha here is in radian. It should be in radian يا شباب. It should be in radian. Otherwise, your answer will be wrong. Now, this is very important, شباب. This is the when the current is in discontinuous mode for the full wave controlled rectifier, okay? Now, load current for controlled full wave rectifier with RL load can be either continuous or discontinuous. Inshallah, we will go through them, and I'm going to explain everything, inshallah, with the continuous and discontinuous mode, current mode, okay? What are the difference between them and how to see them in the waveform. Again, the same thing here, شباب. We have our power supply here. We have S1, we have here S2, we have here S3, and we have here S4, right? This is our load. We have RL load, okay? We will start, let us assume that alpha here is 60 degree, okay? Now, he said something very important. If we need to make sure that it is in discontinuous mode, we need to make sure that that the here يا شباب the inductive load is small enough, okay, and alpha is large enough. Now we will see what do I mean by small enough and alpha is large enough. Now let us see here يا شباب. So after 60 degree, okay, after 60, so alpha here is 60 degree, okay, 60 degree. So after alpha is 60 degree, the thyristor will be on, right? And we will have voltage as we have before. Okay, now this is up to pi, right? Now, the inductive now is very small. Why is that? Because we have small ripple. We have small ripple here, right? So this is small ripple. This is a small ripple. If alpha is bigger, is big enough, it will be like this. It will be like here, okay? If also the inductive load is big, it will be like this, up to here. And also it will be big, it will be like this, and so on. خلاص يا شباب. So now alpha is, we need to make sure that alpha is small enough. Small enough. We will understand inshallah. Don't worry. Now this inductive load is small because it will discharge. It will continue to be like a power supply. When it is positive here, it will interchange the polarity. It will be like a power supply here, and it will retain the small voltage to the supply, right? And we will have small ripple here, right? Now again, after 60 degree, we will have the thyristor. It will conduct, and it will go here up to the negative, and so on, inshallah. Okay. Now this is for one cycle. Now, I said inductive load is very small, right? This is very small. خلاص. I said alpha is large enough. Now what do I mean by alpha is large enough? Now here يا شباب, can you see alpha here? Alpha is 60, right? 60 degree. So what is the difference between here يا شباب? Can you see the difference between here and here? So we have a gap here. Can you see the gap? Let me just use another color. Can you see the gap here? Now we have a gap here. Now if the inductive load is small as this one, ya shabab, and alpha is big enough, then we will have a gap. This gap, I need it in case of discontinuous current mode, because in this gap the current is zero. The current, as you can see here, is zero, right? So if I have a cutoff current here, which is zero, okay, then it is called discontinuous current mode. So if we have this gap, ya shabab, if the gap is there, if we have a gap between the inductive discharge voltage and the second alpha, if you have a gap here, then we will have a discontinuous current mode, because the current goes to zero. If the current goes to zero, then we have a discontinuous current mode. Now let me just explain with this, ya shabab. Can you see here, ya shabab? Now he said, when we have a discontinuous current, we need to make sure that we need to see that you can see that beta is less than alpha plus pi. Now what is beta? Now beta, ya shabab, now beta is here, ya shabab. Now can you see here? Now this is let me just use the green color here. Now this is beta, ya shabab. Beta is from here up to here, right? Now this is beta. He said beta should be less than alpha plus pi. Alpha plus pi. Now this is our pi, right? This is our pi. This is our alpha 2. So here we have alpha at this point. At this point we have pi plus alpha. As you can see here, alpha pi plus alpha is bigger than beta. Beta is here, huh? So alpha, let me just do it again. Maybe it's not clear. Let me just do it again. Now this is beta. So here we have beta. Here we have pi plus alpha at this point. Here we have beta. So alpha plus pi is bigger than beta. Alpha plus pi plus alpha, pi plus alpha is bigger than beta. Okay. And this is called discontinuous mode because the current goes to 0 at this point. And here the current is going to be 0. Now let me just show you how the current goes to 0. Now this is for the voltage, right? So let me just draw it. This is for the voltage. Sorry, this is for the voltage, right? And let me draw the current with the blue color. Now this is the current, right? The current, it will start from here because it is inductive, right? Load, and it will reach to 0. And then it will go from 0, and then it will charge again and discharge, and it will go 0, right? So this is our I out. This is our I out. So can you see here, Shabab, in this point? So the current goes to 0. The current goes to 0. And this is called discontinuous current mode. Inshallah, coming slide, we will see the continuous mode. The current will not go to 0, Shabab. The current in continuous mode will not go to 0. And in discontinuous current mode, Shabab, we know that the V out DC is V maximum divided by pi cosine alpha minus cosine beta. Now this is the formula for V out. Shabab, if you have full wave controlled rectifier, and I said in the example, it is discontinuous current mode, you need to find this formula. If I said resistive load only, you will use this formula, right? If I say a continuous mode, we will see it in the coming slide. Okay, now make sure that you understand, Shabab, when L is very is small enough and alpha is large enough, and I explained that. Now this is for the continuous current mode. For the continuous current mode, this happens when inductive load is large enough and alpha is small enough. Inductive load is large enough because we will have a more discharge voltage, right? Current, sorry, and alpha is small enough. Alpha is small enough. Now let us do it here, Shabab. Again, green color, we'll use it for the voltage. Now let us assume that alpha is 60 degree again. Alpha is 60 degree. And here we can say that at 60 degrees, so this is alpha, right? Alpha is 60 degree. At 60 degree, the thyristor will conduct. This is S1, S2, right? It will conduct, right? Up to here, right? And after that, in the negative cycle, of course, the inductive load here will be like source, right? So it will discharge. The polarity is going to change and it will discharge. That's why we will have a negative ripple. But now the inductive is very large, right? It's large and it will discharge a huge amount of current, and we will have a voltage up to this point. Up to this point. Now, can you see this point, يا شباب? It is the same point of the next alpha, يا شباب. This is alpha 2. So it is discharging until it reaches alpha 2 يا شباب. So alpha is small enough in order to begin the second pulse, which is for the S3 and S4. Now, can you see it here يا شباب? It will conduct from here. Okay, so it will go to 0, right? And also it will start conducting for the second two thyristors. And again, it will, because of the inductive, it will go to the negative rebel, right? And it will start again. And so on. Okay? This is for the voltage. Now, let us see the current. And let us prove that the current is continuous. Now, this is the starting at alpha. So we will have current, right? We will have current. Of course, we will have current from here. It will charge the current through the inductive load. It will charge the current. But now, is it going to stop here? No. It will not stop at pi. It will stop at what? At what, شباب? At here, at the new beta. The new beta. Where is the new beta, شباب? This is the new beta. The new beta is alpha 2. So it will start again. That's why it will start again. And up to the alpha 3. And it will start again. As you can see, of course, now here, يا شباب, it will not go from 0. So it will be like this. So it will not touch 0, يا شباب. It will not touch 0. And so on. Okay? So once we have a discharge current, and alpha is perfectly reaches at the same point of the discharge current, then it will conduct again, and we will have a current, and it will discharge until alpha 2, and then alpha 2 is triggering the second and the third and fourth thyristor, and it will conduct current. The current will never go to 0, right? The current in this part now is not going to 0. This is I out. This is I out. That is why it is called continuous current. So when we have current that does not go to 0, then it means we have a continuous current. Because alpha is small enough in order to switch on the second pulse for the thyristors, and it will charge the inductive load. So after that, the inductive load, it will discharge until it reaches the second, or the neighbor alpha, and it will charge the inductive load again, and so on. خلاص? So the boundary between the continuous and discontinuous current occurs at beta. Now beta, يا شباب, as you can see, beta is pi plus alpha. Now let me do it here with another color, يا شباب. Let me use the orange. Okay. Now this is alpha, right? This is pi. Here we have pi. Here we have pi plus alpha. In this point we have pi plus alpha, right? So as you can see from the current here, شباب, so it will start and stop at beta. It will stop at beta. So beta is basically pi plus alpha, right? So if we have beta is equal to pi plus alpha, then it is continuous current. So the current when pi plus alpha must be greater than the current there should be greater than 0 for the continuous current operation. Now this is the format. So if I ask in the exam, give me the V out once we have full wave controlled rectifier in continuous current mode. So you will use this formula. So this is for the continuous current mode. It should be clear يا شباب this lecture, and inshallah we will go now through the example, and we will finish with this example. This is example 4-6 in your textbook in chapter number 4. This is for the controlled full wave rectifier with resistive load. Now again here يا شباب, the question must say that it is for the is it for the controlled or uncontrolled. Now this is for the again for the controlled. He is giving you the input voltage, which is 120 VRMS, and at 60 hertz with 20 ohm resistor. The delay angle, now he is giving you he's giving you the delay angle, the alpha. So alpha here is 40. Determine the average current, the power absorbed by the RMS, and the source volt ampere, which is the apparent power, right? Now we know that from this controlled bridge rectifier, that the V out here يا شباب is V maximum divided by, because it's the resistive load, right? V maximum is root 2 multiplied by 120 divided by 1 plus cosine alpha. Alpha is here is 40, so this is the answer. This is I out, right? This is I out is 4.77. This is the average current of the load, okay? Now, in order to find IRMS, we need to use this formula and make sure that يا شباب you again find alpha. Alpha should be in radian, right? So we will use this formula to convert 40 degree into radian. So we multiply by pi divided by 180, right? So we can apply the numbers here يا شباب, and you will get 5.8 ampere. This is the RMS. So to find the P out يا شباب, RMS, it is I square RMS multiplied by R from circuit 1 يا شباب, and it is 673 watt. Now the RMS current is already given. It is the same as the source current. It is 5.8, right? And we multiply by VRMS, which is 120. So 120 multiply 5.8, so it is 696 volt ampere. Now if we need to find the power factor, we can just divide active power divided by apparent power, and it is 0.967, which is very good power factor. So remember in the half wave, we have got 0.6 power factor, which is very low, right? Because we are rectifying half of the input voltage, but in full wave rectifier, we are converting the two pulses, the positive and the negative, right? That's why, and we didn't have very much losses, right? That's why our the power factor is very high, which is 0.96. And of course, why we have here a bigger value, not like the normal one, because we don't have here inductive load. This is the resistive load only. We know that S is the addition between the active and reactive power, right? Because we don't have here reactive power, so it is almost the same as the power output RMS. So they are almost the same, right? So we don't have much losses. That's why we have a huge or a very good power factor. Now this is all for our lecture today. Thank you so much for attending this lecture and stay safe.